Hello! Today we're going to explore a powerful and versatile way to describe motion and curves called parametric functions. Our main goal is to help you be able to construct a graph or a table of values for a parametric function. By the end of this lesson, you'll understand what parametric equations are, how to generate points from them, and how to graph them on a coordinate plane. So, what exactly is a parametric function? Let's start with a standard function you're familiar with, like y equals 2x plus 1. In this equation, y is directly defined as a function of x. We can pick an x value, and the equation tells us the corresponding y value. A parametric function works differently. Instead of defining y in terms of x, we define both y and x in terms of a third variable, which we call a parameter. This parameter is almost always represented by the letter t. Think of it as an independent variable, like time. As t changes, the values of x and y both change, giving us a point x, y that moves through the plane. We can think of this as a single vector function, f of t, which outputs a point or vector in the plane. In other words, the location of our point depends on t. So, instead of a direct relationship between x and y, we have an indirect relationship, with the parameter t acting as the bridge between them. This makes parametric functions incredibly useful for describing motion or complex curves. The first skill we need to develop is constructing a table of values for a parametric function. This is the most straightforward way to understand what a given function looks like. Our goal here is to create a table that shows us a set of t values and their corresponding x and y coordinates. Let's work through an example. Consider the parametric function f of t equals 3t plus 2, 4t minus 1. Here, our parameter is t. Let's create a table for t values from -2 to 2. We'll set up a table with columns for t, x of t, y of t, and the resulting point, xy. Let's start with t equals -2. We substitute -2 into both x of t and y of t. First, for x, we get 3 times -2 plus 2, which is -4. For y, we get 4 times -2 minus 1, which is -9. So, when t is -2, our point is -4 minus 9. Now let's try t equals -1. X of -1 is 3 times -1 plus 2, which is -1. Y of -1 is 4 times -1 minus 1, which is -5. This gives us the point, -1, -5. Next, for t equals 0, we have x of 0 is 2, and y of 0 is -1, so our point is 2 minus 1. This gives us a point, 2 minus 1. Continuing the pattern, for t equals 1, the point is 5, 3, and finally, for t equals 2, the point is 8, 7. Let's complete our table with t equals 1 and t equals 2. And there you have it, our complete table of values. We've successfully used the parametric equations to generate corresponding x and y coordinates for each value of t. This table is a set of points that lie on the graph of our function. Now that we have a table of points, our next objective is to construct the graph of the parametric function. The process is similar to graphing a standard function, but there's a crucial difference that relates to our parameter, t. Using the points from our table, let's plot each one on a coordinate plane. First, plot -4 minus 9, then -1 minus 5, then 2 minus 1, then 5, 3, and finally 8, 7. Now, here's the key. We don't just connect the points in any order. The parameter t provides an orientation, or a direction, for our curve. The rule is to connect the points in the order of increasing t. This gives our graph a direction. We connect the point for t equals -2, to the point for t equals -1, then to the point for t equals 0, and so on. To show this direction on our graph, we add arrowheads along the curve. The arrowheads point in the direction that t is increasing. This is called the orientation of the curve. Think of this as a path. The parameter t represents time, and the path shows the position of an object as time passes. The arrows tell us the direction of travel. Because we restricted t to the interval from -2 to 2, our graph has a definite starting point at -4, -9, where t equals -2, and a definite endpoint at 8, 7, where t equals 2. This is called the domain of the parametric function. So, to recap, you plot the points from your table, but then you connect them specifically in the order of increasing t, and use arrows to show that orientation. This creates the graph of your parametric function. Let's work through another example. Sometimes, the parametric functions involve trigonometric expressions. Consider the function f of t equals 3 cosine t, 3 sine t. We are given a domain for t from 0 to 2 pi. Remember that 2 pi radians is the same as 360 degrees. Just like before, we'll create a table of values. For trigonometric functions, it's common to choose key angles on the unit circle to make the calculations easier. Let's use t values of 0, pi over 2, pi, 3 pi over 2, and 2 pi. First, for t equals 0, we have x equals 3 times cosine of 0, which is 3 times 1, or 3. And y equals 3 times sine of 0, which is 3 times 0, or 0. This gives us the point 3. Next, for t equals pi over 2, x equals 3 times cosine of pi over 2, which is 0, and y equals 3 times sine of pi over 2, which is 3 times 1, or 3. The point is 0, 3. For t equals pi, the point is negative 3, 0. For t equals 3 pi over 2, the point is 0, negative 3. And for t equals 2 pi, we return to the point 3, 0. Let's see the full table. Here is our complete table of values for one full period of the parameter t. Now let's graph this second example, f of t equals 3 cosine t, 3 sine t. Using our table of values, we'll plot the points. Start at 3, 0, then 0, 3, then negative 3, 0, and so on. Notice that the point 3, 0 appears twice, for t equals 0 and t equals 2 pi. Again, we connect the points in the order of increasing t, which is counterclockwise for these points. Connecting these points reveals a circular path. Since our path forms a complete circle, the start and end points are the same. We draw an arrowhead to show the counterclockwise orientation of the curve. The parameter t starts at 0, which corresponds to the point 3, 0. As t increases to 2 pi, our point travels once around the circle and returns to its starting position. This specific parametric function, 3 cosine t, 3 sine t, describes a circle of radius 3, centered at the origin, with a counterclockwise orientation. Let's summarize what we've learned today about parametric functions. We started with our objective, to be able to construct a graph or a table of values for a parametric function. We saw that parametric functions define x and y coordinates using a third variable, the parameter t. We learned a two-step process to graph them. First, create a table of t values and their corresponding xy points. Second, plot those points on a coordinate plane and connect them in order of increasing t, indicating the curve's orientation with arrows. We also noted that the domain of t defines the start and end points of our graph. You have now met the learning objective for today. You can now build tables and graphs for parametric functions. Thank you for watching.